508 meters of steel and concrete, 380 piles driven into bedrock, a 660-ton steel pendulum hanging inside the crown. This is how Taipei built the world's tallest skyscraper on top of an active fault line. The site sits in Xinyi district, on soft alluvial soil less than 200 meters from a seismic fissure. Surveyors mark out the rectangular footprint with theodolites and stakes. Trucks roll in carrying rebar, formwork panels, and the first pile-driving rigs. Engineers from C. Y. Lee and partners check coordinates against the master plan. The tower will rise as 8 stacked tiers of 8 floors each, a bamboo silhouette borrowed from Chinese tradition, chosen because the number 8 signals prosperity. But the shape is also engineering. It distributes wind load, breaks vortex shedding, and stiffens the upper sections against lateral sway. Before the tower can rise, the ground has to be made trustworthy. Crews drive 380 reinforced concrete piles 80 meters down through soft soil and into solid bedrock. Each pile measures roughly 1.5 meters in diameter. Together, they form a raft of anchors capable of carrying nearly 700,000 tons of finished structure. Above the piles, workers pour a thick reinforced concrete mat that ties the foundation into a single block. The site is also dug 5 stories deep to make room for parking, mechanical floors, and the lower portion of the building's structural core. Soldier piles and tiebacks hold back the surrounding earth. Pumps run day and night to keep the pit dry. Engineers know the math is unforgiving here. Anything that fails at the bottom will be magnified 500 meters up. Foundations are not the glamorous part. They are the part that decides whether the rest is possible. With the foundation set, attention turns to the central core. Taipei 101 carries its loads through 2 systems working together, a reinforced concrete core at the center and a perimeter ring of mega columns wrapping around it. 16 exterior columns make up the perimeter, but 8 of them, the so-called super columns, are the real workhorses. Each is built from welded steel boxes filled with high-strength concrete pumped under pressure to fill every void. The combined column measures roughly 2.5 meters wide at the base. Crews assemble the steel boxes in sections, lift them with tower cranes, weld the joints, and then pump in concrete from below. The mix is rated at 10,000 pounds per square inch, strong enough to carry the upper floors without bulging or creeping. The first floor plates begin to form a footprint. The building stops being a hole and starts being a tower. As the core climbs, the steel skeleton takes shape around it. Outrigger trusses, diagonal steel braces 2 stories deep, connect the central core to the super columns every 8 floors. These outriggers are what let the building share lateral force between its 2 structural systems. Without them, the slender core would flex too far during a typhoon, and the perimeter columns would carry uneven load. With them, the tower behaves like a single stiff tube. Crews install the trusses level by level, bolting and welding the connections in place. Workers move through the open floors on temporary catwalks. A self-climbing formwork system rides the core upward, casting fresh concrete in repeating cycles. The first tier of the pagoda design closes off, and the second begins to taper outward, the signature flared shape that gives Taipei 101 its silhouette starting to become visible from the street. By the time the structure passes the 40th floor, the construction sequence has become a rhythm. The core leads. The super columns follow 2 or 3 levels below. Floor plates and outrigger trusses tie everything together. Tower cranes climb with the building, jacking themselves up on the completed steel. Materials arrive on tight schedules, steel sections from Japan and Korea, concrete from local plants, glass panels from Germany. Every component is tagged, tracked, and lifted in sequence. The tower is also wired with sensors as it rises. Accelerometers, strain gauges, and GPS receivers will let engineers monitor how the structure breathes in real wind, real earthquakes, real heat. Taiwan averages 3 to 4 typhoons every year and sits on the boundary between the Philippine and Eurasian plates. A building this tall cannot afford to guess at its loads. Every floor confirms what the models predicted. Near the top of the tower, between floors 87 and 91, crews install one of the most distinctive pieces of engineering in the building. A steel sphere 5.5 meters across, weighing 660 metric tons, is assembled from 41 stacked steel plates and suspended on 8 thick cables. Below it sit 8 viscous dampers that look like enormous shock absorbers. This is a tuned mass damper, and its job is to fight sway. When the tower leans into a typhoon or shudders during an earthquake, the sphere swings in the opposite direction, absorbing energy and bleeding it off as heat. The Taipei 101 damper was, for years, the largest of its kind on Earth, and unusually it sits in plain view, visible to visitors from an observation deck wrapped around it. Most dampers hide in mechanical floors. This one is part of the tour. Above the damper, the upper tiers of the bamboo profile finish taking shape. Each tier of 8 floors flares slightly outward from the one below, giving the tower its segmented silhouette and softening the wind forces that would otherwise concentrate on a smooth shaft. Wind tunnel tests in Canada had shaped the geometry years earlier. Corner notches were added, edges rounded, and the spacing of the tiers tuned to disrupt the vortices that try to form along tall, flat surfaces. Workers continue welding column splices and bolting floor beams, while glaziers begin sealing the lower facade behind them. By 2003, the tower has surpassed the height of every existing building in Asia and is closing on the record held by the Petronas Twin Towers in Kuala Lumpur. The climb is not over. The most exposed part of the build still lies ahead, at the top. On March 31, 2002, an earthquake of magnitude 6.8 strikes during construction. 2 tower cranes on the upper floors fall to the ground. 5 workers are killed. The half-built tower itself, however, sustains no structural damage. The engineers' calculations hold. Work resumes and crews begin to assemble the spire. 60 meters of tapered steel sections are lifted, welded, and bolted to the top of the structural roof at 449 meters. With the spire in place, the building reaches its full architectural height of 508 meters, or 671 feet. The pinnacle is more than ornament. It houses transmission equipment, lightning protection, and a small tuned mass damper of its own to keep the spire from whipping in high wind. Each system has a backup. Each backup has a sensor. Each sensor has a log. The lessons of the earthquake are written into every connection above. With the structure topped out, the building begins to close itself in. The curtain wall is a double-glazed system with a heat-reflective coating, blue-green in color, designed to cut solar heat and resist the impact of wind-driven debris. Each panel is unitized, fabricated complete with frame and seals in a factory, then craned into position and clipped onto the steel. Inside, contractors install 34 double-decker elevators built by Toshiba. 2 of them, serving the observation deck, travel at 10 meters per minute, nearly 60 kilometers per hour, and were the fastest in the world at opening. The cabins ride on pressurized cars to keep ears from popping during the ride upward. Mechanical floors stack between the tiers, holding chillers, transformers, and pumps. By late 2004, the lower floors are already being fitted out for tenants preparing to move in. On December 31, 2004, Taipei 101 opens. Fireworks launch from its tiers, climbing the bamboo silhouette in sequence. For the next 6 years, until the Burj Khalifa surpasses it in 2010, it stands as the tallest building in the world. Inside, the 660-ton damper hangs quietly between floors 87 and 91, ready to move when the tower moves. Outside, the tiered glass shaft has become a fixed point on the Taipei skyline and a recurring stage for the city's New Year displays. The tower carries roughly 12,000 workers and residents on a normal day. It survives typhoons, earthquakes, and the daily expansion and contraction of half a kilometer of steel and concrete. From a soft patch of ground near a fault line, engineers raised a structure designed not just to be tall, but to stay still. Taipei 101 still stands. It still does not sway.